Good morning, students. So we define today the concept of countability of sets. Let me recall yesterday in the previous lecture we denoted a set n sub k, and this is the set of first k natural numbers. And based on this set, a characterization of finite sets was given that a set X is finite if and only if either X is empty set or X is equivalent to n sub k for some k in n. And whenever we have this situation that we have a finite set, if X is equal to empty, then we say that X has 0 elements, and whereas when that X has 0 number of elements, and if X is equivalent to some nk, this is always true whenever X is a finite set, then we say that X has k elements. So this is the way how we count the number of elements in a finite set. How you know that how many elements does the set have. Now we define another type of sets, another class of sets that is known as countably infinite sets. So what are countably infinite sets? Countably infinite sets will be also called as denumerable sets. And these are the sets which are equivalent to the set of natural numbers. X will be countably infinite if X is equivalent to set of natural numbers. That means we can put the elements of X in one-to-one correspondence with the elements of set of natural numbers. As you already know that this relation is an equivalence relation, so it is a reflexive relation, and hence set of natural number is equivalent to itself. This is always true for any set. That means the set of natural numbers is a countably infinite set. And also we have shown that this set of integers is equivalent to set of natural numbers. That means, so this shows that set of integers is also a countably infinite set. And indeed set of rational numbers is also equivalent. This will be shown later on, but it is a part of assignment also. That set of rationals is equivalent to the set of natural numbers. So this, from this it follows that this set of rational numbers is also a countably infinite or denumerable set. So there are now two classes of sets. One is finite sets and another is countably infinite sets. Countably infinite set. If we combine these classes, and the combined class is known as set of countable sets, or any set which is either a finite set or a countably infinite set is known as a countable set, and if there is some set which is not countable is known as a uncountable set. For example, set of real numbers, set of irrationals are uncountable sets, but it requires a proof, it requires further verification to establish that this set of real numbers is actually an uncountable set. This will be done at the later stage. But first, we give another equivalent definition of this countably infinite sets. And the equivalent definition of the countably infinite sets is that a set is countably infinite or denumerable. This is the alternate name of countably infinite sets, if and only if its elements can be put in the form of an infinite series of elements. But let me recall what is a sequence. You know, a sequence is any function whose domain is set of natural numbers, and if n is any natural number, then its image f of n is called the term of the sequence, and usually denoted by x sub n, but I a n or anything, but n is kept as there's a subscript, and the sequence f, that is the function f, is denoted through its terms. These are some notations, and there are other notations also. For example, some people denote sequence by simply by using these brackets, small brackets. We are using these curly brackets to denote the sequence. So now, after recall of sequences, let's go uh, and talk about this equivalent definition of the countable sets. It has two parts. Direct part, we first suppose that the set is countably infinite. Then by definition, this set, when you say that it's countably infinite, it has to be equivalent to the set of natural numbers. Equivalent to numbers means you have a bijection from set of natural numbers to the set A. That is a bijection. That also means that each element of A has a pre-image, and all distinct elements have. So also for each in an corresponding image, which we give a notation, and in this way, what we can see now that since this onto function, the subject, so A is the function. A is full range of this function. This is f of n. So definition of f of n says that natural numbers in order. Let's This has to be f of 1, f of 2, so on up to, and f of 1 kept as a1, f of 2 kept as a2, so on up to. So this, so that means a is being represented as a1, a2 in a sequential order, and this is a sequence. This is its elements of a are sequential order, and these are distinct elements. Why they are distinct elements? If you choose a, I, and aj, and if their indices are different, I and j are different, so then the elements are also different. Why they are different? Because indices are different means of these indices, fi cannot be equal to fj, since f is a 1 function, but the image of fi is ai and image of fj is aj. Therefore ai and aj are different. So direct part is clear. Once you have a countably infinite set A, you can always put the elements of this set in the infinite sequence. Now let's look at its converse. When we have this set A, it's are given to us in the form of an infinite sequence of distinct elements. We like to establish that this set is a right set, and for that we need to establish that this A is equal to set of natural numbers, and we construct a bijection for that purpose from set of natural numbers to the set A as follows. For each natural number n, we since A has this A1, A2, A3, AN, so on. These are the elements in A, and for n, you have A sub n, and this A sub n is the image of n, and the function given notation is g. And look at the, we look distinct elements under G. These are the images of N1 and N2 respectively. So images of N1 and N2 and respectively, N1 and N2 under G are distinct. So this proves that this G is a function. We have to establish that this G is onto function. When you want to show that this is an onto function, you choose any element y in A, but you know what are, when you say y in A, that means y is some element of this form an, and when there is a and as a subscript of this A. So this n number. And if you look at the definition of G, by definition of G, what should be G of n? G of n has to be A n, but A n is Y. So this establishes that whenever you choose an element Y in A, you've been able to find a natural number n whose image is Y. That means every element in A has a pre-image. No element is left without any pre-image. Every element is an image of, means this range of G is as a is complete A, and G is a two function. We have already established that G is a one function. So G is a bijection. If G is a bijection, that means A is equivalent to set of natural numbers, and by definition of countably infinite set, it follows that this is countably infinite. Now, this is another concept. Based on this concept, we have some exercises. Result that this is a infinite set contains a denumerable. There is a previous lecture. What is the construction? Let me recall the construction here for you. Let me share this. Okay, let me share the. These are some other exercises. They have been kept as an assignment, but I'm bit explain this. Just let me consider the board. So how you going to talk about that screening? I need to share. Okay. So what we have to establish? We have to establish countably infinite set. So let X be an infinite set, then by definition, as X is equivalent to one of its proper subset, but we don't require that definition. What we require the concept that obviously when you say that X is an infinite set, is a non-empty set, we choose X1 in X. We can choose X1 X. Then if we take out this one element out of this X1, then what remains to us is again an infinite set. If it is again an infinite set, you will have an element here. You will have infinitely many elements indeed in this set. So again, we choose x2 in x minus x1. And since this x minus x1 is an infinite set, so if you take out another element out of this set, that set still remains an infinite set. Then if we take element x2 out of this set, but this set can be equivalent, this is actually equal to this set, taking out, this is equivalent to taking out two elements from set X, and it remains still an infinite set. This is an infinite set. So in this way, what we can again at the next stage, we will take out element, because this is an infinite set, we will have another set, we have element in this set, and I can choose one element out of this set, x minus x1 and x2, and then in this continuing in this way, after k steps, we have x1, x2, so on up to xk. we have chosen these k elements such that x minus x1 x2 so on up to xk is an infinite set. If we proceed through induction, and then we can choose, since this being an infinite set, we can again choose xk plus 1 in x, x minus x1 x2 so on up to xk. And since this set from where we have chosen this xk plus 1 is an infinite set, then this is an infinite set, and if we take out one element out of this, which is equivalent to taking out x1 x2 so on up to xk plus 1 out of this set x will is again an infinite set. So in this way, for each natural number, k, there is xk in set x such that x minus x1 x2 so on up to xk is an infinite set, So what I'm going to do, or what going to define, define a set, define y is equal to set of these elements x1 x2 so on up to xk, because you're able to choose this. Now we will establish that this y is a infinite set, and you know this because of this theorem that we just showed, that every element of this, look at this, if once we establish this y as a infinite set and the elements of this y are in the form of a sequence of distinct elements, these are distinct elements, this follows from the construction of this set, and then from this previous theorem it will follow that this y is a countably infinite set and it is a subset of x, and this will establish that this infinite set x contains a countably infinite set. And to define that, to establish that this set is an infinite set, we define a function, let me call this not, this is a shift function, define a function s from y to y minus x1, as how we are defining, I'm defining y of xk is plus 1. So what we are doing, we are shifting right of it by one step. Uh, we are shifting it. X1, according to this definition, as X1 is, this is, let me first write the elements X1, 2, X3. These are the elements. This is 3, this is 4. By definition, X1 is shifted to X2. X2 is shifted to X3. X3 is shifted to X4. Everything is shifted to its right by one step. So in this way, we see that this function is 1 1. This is also on 2, whereas x1 has no pre-image. That's why we have kept this as y2 y minus x, and why it is on 2, writing it analytically, since for distinct elements xk not equal to xj, when you have distinct elements, that means their indices are different because they have been chosen at different stages of this construction of y. So k plus 1 will be different from j plus 1. This further implies that the elements corresponding to these stages, like k plus 1 and j plus 1, cannot be same. They have to be different. If they have to be different, what is the xk plus 1? This is the image of xk. This has to be different from xj. Okay, this established that this function y is s is the shift function is a 1 1 function. Why it is onto? Because if you take let let us take some x and in y minus x1, or even okay, we don't let's not establish that it's a let's not establish that it's onto function. We don't require it. Now what it establishes, that it establishes that this function s from y to its range, whatever range it is, its range is contained in y, but definitely it is contained, it is actually equal, it will be equal, but I don't require it to is a one onto function. Now it's bijection, is bijection. Now any one function from its domain to its range is a bijection. So it's a bijection. This implies that y is equivalent to s of y, and s of y is a subset of y minus x, and y minus x1 is a proper subset of y. That means y is equivalent to its proper subset. When it is equivalent to its proper subset, that means by definition of infinite set, it follows that y is an infinite set. Y is an infinite set. So this establishes that y is an infinite set, and uh, clearly, since the elements are y in the form of a sequence of indistinct elements, so y is countably infinite set, infinite subset of X. This establishes the fact that every infinite set contains a countably infinite subset. This is a very powerful result. And now if you have any questions, I can take on your questions.